Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Hey, today we're going to do an interesting lesson. It's called Energy and Stoichiometry. You're probably going, oh my gosh, there's that word, stoichiometry. What am I going to do? And we're energy? Now remember, we've been talking about exothermic and endothermic reactions, right? So let's review here. So we've got exothermic. So in an exothermic reaction, energy is released, and then the delta H, we call that the enthalpy. I'm not sure we've used this term. The delta H, the change in the heat, the big fancy term is the enthalpy, is negative, meaning the energy is released, right? If it's endothermic, the delta H, the enthalpy, would have a positive value. Now, how do we do this in a reaction? Because remember, reactions, you're predicting amounts in a chemical reaction. So when we're talking about energy and stoichiometry, we're going to predict energies in a chemical reaction, or possibly amounts from energies. Let's do an example. So let's say we've got this reaction. Hydrogen plus chlorine makes HCl. To balance that equation, we needed 2. But we also know that the value of delta H is equal to 184 kilojoules, actually negative 184 kilojoules per mole. Now when I write that out, what you can do is when you think of this, think of the energy. Think of the energy as like a reactant or a product in your reaction. Since it's negative, what that really means, this means plus 184 kilojoules. Now, it does say here per mole. It's per mole in this reaction, so you can just add it into the reaction. If this had been a positive number, you would add it over to this side. Make sense? So this is the balanced equation now with energy involved. Before, we haven't added the energy. So if I have 1 mole of hydrogen and 1 mole of chlorine, which means 2 moles of hydrochloric acid, it will release 184 kilojoules of energy. Make sense? Now, to do a stoichiometry problem, let's say that I start with, I produce 3 grams of HCl. So this is my question, right? Starting with 3 grams of HCl, how much energy will be produced? So put a question mark. So I want to convert from here to here. So this is a little bit different than before, right? So again, we'll start with what we know over 1. 3 grams, let's say 3.0 to get significant digits. 3.0 grams of HCl over 1. Now, this is just what we've been doing already before, grams of HCl. I want to convert to moles of HCl. So I'm going to say grams of HCl to 1 mole of HCl. This is just the molar mass. We've done this a million times. And now I'm going to take my periodic table out and find the weight of HCl. H is 1, chlorine is 35.5, so that'd be 36.5 grams of HCl. Grams of HCl cancel, but I have moles of HCl. Now watch this step. This is the step where we add energy. It's kind of like the mole to mole step. I'm going to say, look, there's a 2 here, so I'm going to say 2 moles of HCl is equal to 184 kilojoules. And that is the answer. Right, you stop there. I asked for energy, so I get my calculator out. Got my calculator out and clear it. There you go. 3 divided by 36.5 times 184 divided by 2, because that's on the bottom, right? And I get 7.6 kilojoules. All right? Let's do one more problem. So we've got the reaction N2 plus O2 makes 2NO. And the value of delta H is positive 180 kilojoules per mole. So where do we put this in the reaction? We put this on the reactant side, so that's plus 180 kilojoules. Notice again, kind of weird, we've almost never lost the unit, but that's per mole in this reaction. All right. So let's say that I'm going to put into this reaction 525 kilojoules. That's my given number. The question mark is how many, let's say, liters at STP of nitrogen monoxide will I form? Okay, so again, our given number is this. So I think the way to really do this, so you understand, think of kilojoules as just another chemical in the reaction. Make sense? All right, so I'm going to say 25 kilojoules over 1. Then I'm going to say, this is like, and think of this as like the coefficient, 180 kilojoules is equal to, look at this, 2 moles of nitrogen monoxide. The kilojoules cancel. One more step. I want to go from moles to liters. I'll say 1 mole of NO is equal to 22.4 liters of NO. Gosh, I'm using the mole map to solve that problem, right? The moles of NO cancel, and I just get my calculator out, right? And I'm going to just take, what would it be, 525 times 2, right here, right? Divided by 180, right? Times 22.4 gives me 131 liters of NO. So you can start with energy and go to like liters or grams or whatever, or you could start with liters or grams and go to energy. Just think again, woo, I'm dropping everything. Just think of this right here, right, as like a coefficient, the 180, and the kilojoules like just another chemical. And that's how you do energy and stoichiometry. Houston, we don't have a problem.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.